Okay, in this section, we study the connectedness under the intermediate value property. Okay. First, we will give some definition. Let A be a subset of Rn, and we say that two open subset U and V separate A if both of them have no empty intersection with A. And the intersection of A and U and V is empty, and the union of these two open sets contain A. Okay, so the UV satisfies the following condition. No empty intersection with A means the intersection is not empty. And the intersection of A and UV are empty, and the union of, sorry, this is a misprint. This is V here. No. So these two conditions can also these two can also is equivalent to the intersection of U and V has empty intersection with A and V. Obviously, from the first the intersection of the three is empty, we get this empty. And also the second condition is equivalent to A, maybe A is the union of the intersection of U and A and V and A. Okay, so our condition for the separate, that is the start condition here, is equivalent to say that the set A can be split into two parts. Both parts are the intersection of A and an open subset U and V. Okay, so but I remind you that U and V can has no empty intersection. U and V can has no empty intersection, but their intersection with A has empty intersection. Okay. Okay, this is the concept of separate. Okay, using this separate, we can define what we call connected definition. If there do not exist open sets. Separate A. Then we say that A is connected. So this connected is different from the previous pathwise connected. We will see that pathwise connected subset is always connected, but there are examples which is connected but not pathwise connected. Okay, so before this we study the relation between connected and the intermediate value property. We have proved that pathwise connected set has intermediate value property. But we also mentioned there are subset of Euclidean space which has intermediate value property but not pathwise connected. Okay, now the new concept we just introduced, the connected, is equivalent to the intermediate value property. So this is our theorem. A subset A is connected if and only if A has intermediate value property, IVP for short. IVP is the abbreviation of intermediate value property. Okay, so this is the main theorem of this section. So this is again if and only if. So we need to prove this theorem in two directions. First, we prove this only if part. We know that A is connected. We want to show you that A has intermediate value property. So if this is not true, we argue by contradiction. If this is not true, then A do not have intermediate value property. This means we can find a continuous function defined on A whose image is not an interval. If this is not true, then there exists continuous f function defined on A such that the image of this f is not an interval. Okay, so the image of fa is not an interval. This means A, B, and C real number. Maybe not A, B, C. I don't want. The image is not an interval. This means there are some number C here. We have a value of f less than C. We also have value of f greater than C. But C itself is not a functional value of f. C is not a value of f at any point. Okay, so this means there exists a C real number such that C is not a value of the function, and the pre-image of this open interval is not empty. This means f has value greater than less than C, and also this is also the pre-image of C positive infinity is also not empty. This means f has value greater than C. Okay, we have a C has this property so that these two sets are not empty. So we claim that there are open sets U and V such that the preimage of this is equal to the intersection of A and U, and the preimage of this is exactly the intersection of A and V. Okay, we claim there exist two open sets. Once we can find such two open sets, what can we say? We'll prove this claim later. Okay, then the intersection of A and U and V, what's this? This is the intersection of the preimage of this is the intersection of A and U and okay, the intersection of A and U and V equals the intersection of A and U. That is the preimage of minus infinity C, and the intersection of A and V, which is the preimage of say positive infinity. Okay, but this is obviously empty. Okay, this is the first conclusion. The second conclusion, A, of course, A is the union of this. Because C is not a value of F, therefore there is no point in A whose value is C. No X in A, so that Fx equal to C. Because C is not contained in the image of F. So from this fact, we can see that A is the union of these two. But what's this two? The first one, as our claim, the property of U and V, the first one is exactly the intersection of A and U. And the second one is A and V. And A and U is a subset of U. A and V, the intersection of A and V is a subset of V. Therefore, this is a subset of the union of U and V. Okay? So these two things tell us that A is not connected. From this, we see that U and V separate A. A is not connected. Okay, so this is a contradiction to our assumption on the connectedness of A. Okay, so this proves that once A is connected, A must has the intermediate value property. So our only if part of the theorem, is proved. But we are missing something. We still need to prove our claim, right? The open sets U and V, the existence of U and V are similar, so we only prove the existence of U. So in summary, our proof for the only if part only leave one thing, to prove the existence of U. Of course, similarly, we can get the existence of C. So in the next page, we will finish this